Right guys, see this question. See this question. Can a 50 Hz transformer be used as 25 Hz? Yes. Can a 50 Hz transformer used as 25 Hz? They are asking. If the input voltage is maintaining constant at rated value, the voltage is maintaining at constant rated value. So can you tell me, is it a fair operation or not? Here comparatively, the V by F ratio is not constant. The flux density is not constant. Flux density is equals to V by F. Here the frequency is reduces, so the flux density increases, ultimately flux increases, ultimately I mu increases, etc. will take place. So let's see the questions. Yes, actually don't use like this first of all, because it may lead to saturation problems, etc. Okay now? So no, owing to decreased reactance of the transformer, input current will be doubled at load. Generally, it may not that much of impact on that. Generally, the I mu and no load currents will be impacted more. No, the flux will be doubled. Yes, the flux will be doubled. When this is halved, this will be doubled. The flux will be doubled, which drive the core to excessive saturation. The core gets into saturation. This is your answer. Right? Next. A transformer has maximum efficiency. The transformer has maximum efficiency. Nothing but the iron losses to full load copper losses ratio with root is equals to 3/4 of load. X they given 3/4. The ratio of iron losses and full load copper losses is square on both sides. Iron losses and full load copper losses. Iron losses and full load copper losses is equals to square on both sides. This is 9/16. 9/16 is your answer. Yes or no? Iron losses and full load copper losses they asked. Next one. 440 volts by 110 volts single phase transformer has primary resistance. Primary resistance 0.03, secondary resistance 0.022 ohms respectively. This is the 440 by 110. So K is equals to E2 by E1. K is equals to 1/4. Iron losses at normal input. Iron losses they given as 150 watts. The secondary current, they are asking the secondary current at which the maximum efficiency will occurs. At which the maximum efficiency will occurs. Okay guys, the secondary current at which the maximum efficiency will occurs. So generally the maximum efficiency will occurs when the copper losses equal to iron losses. Now they are asking with respect to secondary. So with respect to secondary, nothing but this is I2 square R2. This is not R2 sir, R02. The total copper losses. The total copper losses will be equal to iron losses. Not only the secondary copper losses, right? Total copper losses, nothing but we need to take R02. So 150 watts is equals to I2 square into R02. What is R02? What is R02? R2 plus R1 dash. R1 dash nothing but R1 into K square. R2 0.022 plus R1 0.03 multiplied with K square. K square is a 1/16. K square is a 1/16. So what is the answer, sir? 0.022 plus 0.03/16. 0.03/16. I will calculate, sir. Actually, we shouldn't use the calculator, but here we need to utilize this. Okay. So let's see this one time. So 0.03 divided by 16 plus 0.022. So its combined value of 0.023875. 0.023875. Now this is the value. Now 150 divided by 0.023875 is the value I2 square is equals to 6282.722. 6282.722. What is root of 6282.722? Is the value of I2 is equals to 79.2636 amperes. 79.2636 amperes. There is no exact value 79.2636 amperes. We need to take some approximation. You may get this answer. You may get this answer if you calculate exactly. Okay, so once to calculate again 150. This is R1 plus R2 plus R1 dash, which is R02 nothing but R2 plus R1 dash. Here K is equals to E2 by E1. E2 by E1 nothing but this is K is equals to 1 by 4. R1 into K square, K square. So once again I am doing 0.03 upon 16 plus 0.022. So 0.022, 0.023875. This is the value of R02. This is the value of R02. 150 out of 0.023875. This is 6282 something, 6282 something. Then square root of 6282. Around 80 amperes is getting, sir. So it may be answer of 82.8 amperes. This is the secondary current at which the maximum efficiency occurs. The secondary current at which the maximum efficiency occurs at around 80, but they're not given, in the range of 82.8 amperes. Let's go for next question. In a 50 kVA single phase transformer, 50 kVA single phase transformer, iron losses 500 watts and full load copper losses they given. Full load copper losses they given 800 watts. Then the efficiency at 0.8 lagging. Efficiency at 0.8 lagging. Let's calculate. Efficiency is equals to kVA 50,000 into 0.8. 50,000 into 0.8 nothing but 40,000, right? So kVA into power factor plus iron losses plus copper losses. Iron losses plus copper losses. So 40,000 by 41,300. 400 by 413. 400 by 413. Let's calculate 400 by 413. 400 by 413. What is the value? 0. Nothing but 4,000. 9s are 413 9s are 413 9s are how much, sir? 9 3s are 7 2 9 1s are 9 11 36 37. So 3717 almost 283 will be remainder. So this is 9s are. Point is there, so 0. Almost 7s are, approximately 7s are. So you will get this answer. Approximately 7s are. So you will get around 6 times and etc. You may get this answer. Next. Single phase transformer has turns ratio nothing but 1 by K. 1 by K is equals to 1 by 2. And is connected to a purely resistive load. Connected to a purely resistive load. And the magnetizing current they given 1 ampere. Magnetizing current 1 ampere. And the secondary current they given I2 is equals to 1 ampere. I2 is equal to 1 ampere. If the core losses and leakage reactances are neglected, when the core losses neglected, IW is equal to 0. Because there is no core losses, nothing but there is no component, working component. So what is I naught? I naught is equals to IW plus I mu, which is IW plus I mu. There is no IW, so only I mu. I mu is nothing but I mu is nothing but I naught, which is equals to 1 ampere. Now the primary current will be, they are asking the primary current. What is the primary current? I1 is equals to I0 plus I2 dash. I0 plus I2 dash. How it will be? For example, this is V1, this is V2, this is V2, this is flux. Here pure resistive load, so pure resistive load, that's why here the current is I2 1 ampere, and I1 I want, so this is 1 ampere, this is I2 dash. What is I2 dash? I2 dash is equals to K into I2. K is equals to 2 and I2 is equals to 1. K is equals to 2 and I2 is equals to 1. So I2 dash is equals to 2. And this is our I mu. I mu is equals to 1 ampere. I mu is equals to 1 ampere. And we need to take sum of these two. Sum of these two is taken as I1, and I2 dash and I mu's are 90 degrees displaced. So simple vector addition, 1 square plus 2 square, 1 square plus 2 square, 1 plus 4, root 5 is your answer. These are the vector sum, not a arithmetic sum, because I2 dash is here, I mu is here. The I mu is nothing but I naught because there is no IW, that's why. So root 5, this is root 2, 2 and root 5. Root 5 is our answer. Root 5 nothing but 2.24 etc. Next question. What is the answer for this question? Can you tell me, guys? During short circuit test, the core losses are negligible. This is because during short circuit test, the voltage V is equal to short circuited voltage in the range of only 10%. Voltage is very less. The iron losses are depends on voltage, so which are very less, which are negligibly small. You know this. Options. The voltage applied across the high voltage side is a fraction of rated value, and so it is mutual flux. The current on the low voltage side is very small. This is wrong. The iron losses fully saturated, wrong. The power factor high, wrong. So the answer is very fraction of voltage. Next, transformer taken current of 0.6 amperes. Current of 0.6 amperes. 64 watts absorbing. 64 watts absorbing. Primary connected to its normal supply of 200 volts 50 edges. 200 volts 50 edges, and secondary is open circuited. Secondary is open circuited. Nothing but this is W naught. Nothing but this is VI naught cos pi naught. Nothing but this is VI naught cos pi naught. Okay, guys. Nothing but this is I naught. The iron loss component of current. They are asking loss component. They are asking loss component. What is loss component? IW is equals to, what is the formula? Do you know? IW is equal to I naught cos pi naught. I naught cos pi naught. I naught cos pi naught. I naught is a 0.6 multiplied with cos pi naught. What is cos pi naught value? Let's calculate. W naught is equals to V. V is a rated value. I naught is a 0.6. I naught is a 0.6 into cos pi naught. So 0, 0 cancel. 2 3s are 2 32s are 2 10s are 2 8s are, sorry, 2 16s are. So what is cos pi naught? The cos pi naught is equals to 16 by 30. Cos pi naught is equals to 16 by 30. Yes or no? This is 16, this is 30. Cos pi naught is equals to 16 by 30. 3 2s are, 3 5s are. 2 1s are, 2 5s are. So 16 by 25. So just we calculated this value 0.64 I think. 0.64 I think. The iron loss component is 0.64. Any mistake is there? Any mistake is there? 3 2s are. Small mistake is there, sir. Small mistake is there. Let's see here. This calculations 16 by 30, right? So 3 2s are, 3 10s are, sorry, 3 10s are. 3 2s are, 3 10s are. So 32 by 100. 32 by 100 nothing but 0.32. 0.32 amperes. 0.32 amperes is our answer. Small mistake in calculations. Be careful, sir. Next one. Two transformers each having iron losses of Pi watts, Pi watts, and full load copper losses of Pc are put back to back test, Sampana's test, and full load current allowed to flow through the secondaries. Secondaries are carrying full load current in the back to back test. The total input power will be the input power is equals to losses of two transformers. Losses of two transformers. What is losses of one transformer? One transformer iron losses plus copper losses, and other transformer also iron losses plus copper losses, because both are two identical transformers. Both are same transformers. So the answer is 2 times of the iron losses plus copper losses. We discussed this question in the class also. Next. A 5 kVA single phase 50 Hz transformer has 50 watts iron losses, 50 watts iron losses, and 150 watts full load copper losses. 150 watts full load copper losses they given. Its efficiency at 0.8 lagging. Efficiency at 0.8 lagging. Efficiency is equals to kVA into power factor divided by kVA into power factor, kVA into power factor plus iron losses plus copper losses. Iron losses plus copper losses. What is the answer? 4000 is the numerator. This is 4000 plus 200. 4200. Which is the answer is 40 by 42. Which is the answer is 20 by 21. 20 by 21. What is the answer? Approximately 0. 0. Nothing but 200. 21 nines are 189. 189 nothing but 11 will be there. Point is there. So 21 5s are 105 will be there. Another 5 will be there. So 95% plus answer. Simple question, sir. Next one. A single phase transformer has no load losses 64 watts, which is nothing but iron losses given as 64 watts. Obtained from the open circuit test. This is from open circuit test, of course. When a short circuit test is performed at 90% of rated load, this is operating at 90% of load. Flowing in the both LV and LV windings is measured, which is 81 watts of losses. Only 90% of rated current is flowing in primary and secondary, then the losses are 81 watts. The transformer should exhibit maximum efficiency at, the maximum efficiency occurs at X is equal to square root of iron losses to the full load copper losses. Iron losses to the full load copper losses. Iron losses we given 64. What about full load copper losses? What about full load copper losses? We need to calculate. I given one formula. The copper losses to the short circuit losses is equals to I by ISC whole square. I by ISC whole square. What is copper losses? We need to calculate at full load. What is short circuit losses? 81 watts they given. What is full load current? What is short circuit current? What is full load current? What is short circuit current? For example, full load current is taken as I. For example, full load current is taken as I. At 90% of load, the current is, at 90% of load, the current is 90% of full load current. This is full load current, this is 90% of full load current. These two are gets cancelled, 10 will come here. So the copper losses at full load by 81 is equals to 10 square will come here and 9 square is there. These are gets cancelled each other. So the full load copper losses is 100 watts. Actually, you should analyze this without calculation. At 90% of load, you will get 81 watts, nothing but at full load, you may have 100 watts exactly. 9 square 81, 10 square 100. We already discussed this way of analysis. So this is 100. So what is the answer? Root 64. Root 64. Root 64 is a 8. Root 100 is a 10. 8 by 10th load. 8 by 10th load, nothing but 80% of load. At 80% of load, what is the answer, sir? At 80% of the load current, we will get the maximum efficiency. Like a simple questions. Actually, this way of questions are important for us, sir.